So, hello everyone. My name is Xinhui Lai. I'm the first year PhD student. For previously, I was involved in the rescue project. So my supervisor, Professor Maxim Jenihan, my co-supervisor, Professor Yang Rek. My research interests including the actual functional verification topic, which are security, reliability, and quality verification, and also timing and power set channel analysis, which include RTL design and the binary neural network hardware inference engines. So today I'm going to give a presentation about our previous research work, which is early RTL analysis for set channel attack vulnerability in PUF fuzzy extractors. The presentation is based on the publication we have done in the WSS SOC in last year. So in general, the presentation will be divided into the following 7 parts. So first, I will introduce motivation and background. Then I following up with attack model and attack procedure. After that, we propose a methodology. I will explain what's the detail of that. And after that, I will explain the experimental result and draw the final conclusions. So start with the motivation. PUF represents the physical and clonable function. It's kind of gaining attention to the cryptographic community due to its inherent variability in the manufacturing process. It's widely used as a digital fingerprint. However, it's known that PUF is noisy devices and most of the time it's work likely in a noisy environment, and PUF is sensitive to the noisy environment. Thus, somehow it's need error correction mechanism such as a fuzzy extractor. Fuzzy extractor is an efficient way for the error correction. But the recent work also demonstrates that the using of fuzzy extractor kind of, in some terms, it's increased the reliability of the PUF, but also it may enable a new set channels which can be exploited by the attacker to break the PUFs. The object of our work is to verify a given PUF fuzzy extractor's implementation against a defined attack. For the background, I will give a general, briefly introduction about what is a PUF and how fuzzy extractor used for memory-based PUF. So the physical uncloned function is a device that can exploit inherent randomness. This randomness is introduced during the manufacturing, so thus it can give a fingerprint to a physical entity. So it's widely used, can be derived as identifier and the cryptographic key. Compared with the pre-stored key, it provides a significantly higher security assurance since it's easily attached or embedded into the cryptographic implementation as physical devices, and also it's volatile and can be derived only when you require it. So for the fuzzy extractor used for memory-based PUF, the fuzzy extractor serves as a post-processing unit in this scheme. Generally, it has 2 procedures. The first procedure is called generation procedure. It happens right after you first powering on the device. So when you powering the device, it generates a PUF. It generates a response which is W. The W will generate XOR with encoded code word to generate helper data. This helper data normally will store in the non-volatile memory and be used for the following reconstruction procedure. So for the generation procedure, it's only happened once. And after that, in the lifetime you're using these PUF devices, the reconstruction procedure comes to the scheme. So when you're repowering on the device due to the noise, the PUF response will not give the same response as before, as the initial response, which is W. To give you a bit different response, which is W prime. When you XOR with the helper data, it's generated the encoded code word, but with errors. So with the following stage of the ECC decoder, it will help to locate the error and also correct the error to generate the initial PUF value with W. So for the reconstruction procedure at lifetime, it happens at least once. So from attacker point of view, when they want to attack for these PUF devices, the ECC decoder in the reconstruction procedure seems to be the most vulnerable part. And for the following attack model, we are define attack parameter and attack assumptions. The attack model is a combined attack model based on fault injection and timing analysis of error correction code execution. The fault parameter assumed for the physical fault injection are defined as follow. So the first one is the granularity. So when you do the fault injection, the fault injection result in exactly one port in a 1-bit data. When you do for the modification, the fault you are injected to the bit and it's resulting specific logic value. And so the attacker needs to have a bitwise precise control. After that, so once you inject the fault, the injected fault should have a transient nature as well. Following the attack parameter, attack assumptions are summarized as the follow for. So the first one, the error correction implementation should leak exploitable information through the timing channels. The second one, that the internal noise of the memory-based PUF is negligible under a stable environment condition. And the third one, the generated helper data remain constant during the reconstruction procedure. The last one, the attacker has a control access for measuring the decoding execution time. With the predefined attack model, the attack procedure was summarized as follows. The attack procedure is combining the fault injection and the timing side channel analysis. The procedure was composed by the following 4 steps. So when you first powering on the device, you marrying on the recording time T for the non-fault injection memory data. Then you do the fault injection. So you start with the first bit of this memory-based PUF, and you running the decoding time, and you running the decoding procedure, and you record the decoding time for this for the decoding time for after the fault injection. You compare the decoding time with, or you compile the fault injection decoding time with the previous decoding time. If it's different, it means like you inject a different value. The initial value should be different from the inject value. Then you reverse the first bits. So for example, for the first bits of the memory-based PUF, initially it's 0, but you inject 1, and you do the error correction decoding, and you record the time different from the previous one with GTT. You recognize that you inject a different value, so the initial value should be 0. So following this 4th step, you traverse all the bits in the memory-based PUF. At the last bits of the memory-based PUF, you recover all the memory-based PUF data. So in order to tackle the proposed attack, we provide a methodology which is composed by structural analysis and simulation analysis. So in general, the structural analysis of this methodology, the objective of that is to reduce the searching space for the simulation. And for the simulation-based analysis, the objective of that is to verify the given fuzzy extractor error correction code implementation. With these two-step analysis, we have the early conclusion about the design. So for the future or for the next step, we can do the manually design correction or automatically design correction already at RT level, very early stage design phase. So for the structure analysis, we have selected the binary bit stage and read-summon code, error correction code for the study. So from the algorithm based, we think about what should be the controllable primary input for these two decoder, and we're considering how they are implementing the hardware and how those parameters would influence for the execution time, for the decoding execution time. For the binary bit stage is using for the binary bit error correction, as shown in the right top picture. You can see the binary bit stage, they have the 3 components. They have 3 components. The first one is the Sagem calculator, which is to generate the information about the error bits. Then the second stage with the K equation solver for the bit stage, use the Burger-Massey algorithm to use the information acquired from the first stage and to generate the polynomial function, arrow position polynomial function. Then for the chain search, is traverse all the possible value in the Gauss field and to give to searching for the right answer for this equation. Then they have the output to XOR with the input to generate the correct input. So for the Reed-Solomon code, it's a non-binary error correction because it's using for the non-binary, so it's a little bit different from the binary message. So for the key equation solver, they use occluding algorithm sometimes normally, because since they are using for the non-binary error correction, they need to identify the error location as well as error value. That's the reason they have a additional stage called phoning. This stage is used for generate the error values. So based on the analysis of algorithm, we found that for the occluding algorithm stage, this stage may be they require a different number of iterations. This can introduce a different execution times. Follow with the structure analysis, we have generated a stubulin parameter which may introduce different execution time, which are code word value. This is to be noticed that this code word value is a correct code value. They are not include the error values. So the second one is error value, and the third one is the position of errors. The last one is how many, the number of errors. So considering also the relationship of also considering how those parameters from attacker point of view, whether it's vulnerable to the proposed attack, the relationship of the decoding variation caused by manipulating the above parameter and the vulnerability to the proposed attack was summarized in the following table. So as you can see, as in the right circle, we have found like only for the Reed-Solomon decoder, if you input the different number of errors, at this one will show you that the different execution time based on different number, and at the same time, it's vulnerable to the proposed attack. So following with the proposed methodology, the proposed methodology was validated by running the simulation on this 3 case study design. The first two is the binarized BCH decoder with a serial BMA and parallel BMA. The binary BCH have 20 bits code word and 8-bit message, and the Reed-Solomon decoder, they has the 8-symbol code word and 4-symbol message. For each symbol, they are 8-bit. They are 8-bit values. And we have run the exhaustive simulation on this on the binary BCH decoder, and also exhaustive simulation for one code word, one possible correct code word, with all the possibility of the error bits and error values and error position. The simulation result was showing in the right table. I marked the column which has a different execution time. You can see for the different number of errors, when you inject when you run the whole simulation, you can figure out like they have a different timing based on if you have a different number of errors. So come to the final conclusion. So we have provided an attack model based on fault injection and timing analysis of error correction code execution. The aim of this attack is to extract the secret of PUF values. So based on that, we propose an early RTL methodology, which can be used for verifying the verify an error correction code design in vulnerability against the proposed attack. So last, we have demonstrated the timing side channel exists in the case study of the error correction code design. Thank you for the time, and I'm ready for the questions.